Unfortunately, Matt Goodwin couldn't be with us here today, but he did send us a pre-recorded version of his talk. So we are going to play his talk now and hope that everything works.
Hello there and welcome to this presentation. My name is Matt Goodwin and I'm delivering this presentation on behalf of my collaborators who work for AWE in the UK, FOI in Sweden, PNL in the US, Met Office in the UK and EDF Energy in the UK. This presentation is about the analysis of 12 months of radio xenon monitoring array data in the UK. So the data was collected on a network of sauna cube systems which we had deployed around the Hartlepool nuclear power reactor. I'm going to be talking about some of the detections that we've picked up on this network and how we've been analysing the data and attributing the detections to possible sources. A group of collaborators as part of the Xena project came together to study the Hartlepool nuclear power reactor and understand the radionuclide fingerprint of this type of facility. So there are over 300 different nuclear reactors in the world, and in terms of the radionuclide source release parameters, we actually know very little. And this is incredibly important to radionuclide monitoring, to our community, and to the mission of the CTBT. So in this work, we aim to characterize the radionuclide fingerprint of one particular reactor type, which is the Advanced Gas-Cooled Reactor, or AGR. There aren't many of these reactors in the world. They're mostly based in the UK, and one of them is Hartlepool Nuclear Power Station, which has 2 reactors. You can see the photo of when the team was stood on top of one of the power caps at the Hartlepool station. You can find more information on the background of the project and the overall aims and the work that we've been doing over the last few years in the linked publication here as well. One of the main parts of the project was to deploy a sauna cube array around the Hartlepool power station. So you can see from the figure how we configured the systems in the region. Cube 1 was at Bulby, about 24 kilometers east of the reactors, and that was the closest system. Cube 2 was in Durham, which was 30 kilometers to the northwest, and Cube 3 was at Leeds University, which was around about 100 kilometers south. The idea being that this one was a little bit further away. We knew that the background from mainland Europe would be a significant challenge to us, and we hoped that having one system further south and further away from the facilities would possibly catch plumes as they were coming up north from mainland Europe. So here are some of the data from the array. The figure shows xenon 133 activity concentrations with time. And as you zoom in, you can see that for each of the individual elements of the array or stations on the array, you can see where plumes are passing over not just a single sensor, but the array as a whole. So we consider these to be array detections. And this is really interesting. It's logical to assume that where we've got plumes of detections arriving across the whole array, that the source is not local. Given that Hartlepool Power Station was effectively in the center of the array, this was one of the useful distinguishing features of array type data that we're able to use to determine the possible source and certainly exclude some sources. Now, when Hartlepool Power Station undergoes an outage, possibly to refuel one of the reactors, and across the 2 reactors this happens around about 5 times per year. When this happens, they have to depressurize the reactor core, and this results in a release to the environment through a gas processing route. So these are known as blowdowns, these depressurizations of the reactor. And I've labeled one of the blowdowns that occurred in June, and you can see it occurred just before we had a series of detections across the array. And this was one of the periods that we analysed very, very closely from this data set. Interestingly, this one was not related to the blowdown. So thinking about the analysis toolkit that we have at our disposal, when analysing data like this, we can look at the radionuclide data itself. We need to look for anomalies within that data set. We can compare isotopic activity ratios as well. We can then use STACS data. So there was a STAC monitor installed at Hartlepool giving us what we considered ground truth. Can we use that to remove known background interferences. Similarly, we had access to stack data from IRE, which was the biggest source, the biggest nuisance source in the background for us. Of course, we have to use atmospheric transport modeling, or ATM, so we use this in both forward and backward modes. So forward, predict the movement of material in the atmosphere from a known or possible emitter and look at how it contributes to our sensors. And also to backwards or inverse model from a given sample from a given detection and work out a possible source region. We can then try to associate different detections and non-detections that may be related to a given release. And we can put all of this information into source reconstruction software. So in particular, a number of the collaborators were using FRIA to determine source release parameters, i.e. the source magnitude, the location, and the release start and stop time. And we were doing this on background sources as well as on sources that we thought might be related to Hartlepool. So I mentioned IRE being a significant background source. It's well known and well published that this is a big background source in mainland Europe. So IRE provide STAX data through the STAX project, and this data was invaluable, in fact, in determining the impact of IRE on our sensors. So the figure shows for each of the systems on the array, cube 1, 2, and 3, for the whole, most of the year, you can see the measured Xenon 133 activity concentration in black versus the predicted or simulated activity concentration of Xenon 133 from IRE. And you can see that a lot of the features that are represented in the time series are mirrored between the measured and the simulated. So here, overall, whilst there are some differences, particularly in magnitude of some of the detections, which usually are related to complex atmospheric conditions, overall, there is a very good agreement, particularly in time. So when a plume arrives as predicted from IRE, and we get detections at the same time, it's very clear to the eye and very useful to be able to see that, well, those detections, whilst the magnitude may be slightly off, are most likely related to the releases from IRE. It's also perhaps even more beneficial to see where there are measured detections with no simulated contribution from IRE, and these prompted further analysis. We also had stack data available from Hartlepool itself, available in two forms. We had measurements of the gaseous activity in core during the powered period and also during the blowdowns. So we could see the activity of the coolant gas in the reactor being reduced as the blowdown occurred. We're also measuring the activity concentrations of gases at the stack through a stack monitor. Both of these are based on high purity germanium detector systems. And the inputs from these measurements were used with atmospheric transport modeling. So the Met Office were able to run atmospheric transport models at very, very high fidelity. So the Met data input that went into these is down at around about 1.5 kilometers on a very, very dense sampling grid. And we were able to track the movement of these releases and compare those with the measured detections on the cube to see if we could positively tie detections on the cube network to releases from Hartlepool. So we're showing some of the plume movement for the March 2022 blowdown, which was the first one that we were measuring for, and also in June 2022, when we thought we saw some detections, but actually turned out they were from IRE. March 22 represents a very interesting period on the cube array. So in the figure, you can see the Xenon 133 activity concentrations at cube 1. You can see where we've attributed to various different source sites, and these are based on some input information. So we have some information from reactors such as Heysham in the UK on when they were emitting, and we have some information from stacks on when IRE was emitting, and then filling in the gaps, we were able to determine possible source attributions based on other more generic ATM tools. But in this period, in this what seems like one broad plume of detections, we were able to attribute a number of different sources, and one of those was Hartlepool. There was a detection of around about 7 millibecquerel per meter cubed of xenon-133, and it was only seen on one system. And this system, the measurement agrees incredibly well with the ATM and stacks-led prediction. So you can see the purple is showing the simulated activity concentration, which matches incredibly well with our one measurement. This was our one and only positively attributed detection to Hartlepool throughout the whole year that we were sampling in the UK. There were also a number of other detections across the cube array that were clearly not related to a local source and also weren't explained by the IRE forward simulations. So each of these were investigated in more detail to determine if there was another source in the background. One of those was in December 2022, where there were a series of significant detections across the array. These also coincided with significant detections across the Swedish cube array and on the IMS. Here we used the measurement data and also atmospheric transport simulations from those collections to determine release parameters, possible release parameters using a Bayesian tool known as FRIR. And you can see that the release magnitude must have been fairly significant, around e to the 13 becquerels of xenon-133, and it's fairly well contained the release start time and the release stop time and come up with a likely source. We believe this was a release from a power reactor in this region. This of course leads us to consider whether there are benefits in terms of source location and attribution of using an array versus a single sensor or single station like we have on the IMS. So using multiple detects and or non-detects can help constrain a source location and the release parameters. Using the set of detections from December 2022, which I've just shown you, the probability density functions show how the uncertainty in source parameters is reduced when using array type information, and this is compared to a single sensor. So the frequency distributions that you see on the figure here show for in blue where we used a single sensor versus multiple sensors in the array, giving you the results in red. So where does this leave us in terms of the xenon-133 in particular that was measured throughout the radioxenon life cycle? Well, we've got measurements of the core coolant using the GAM system, and there's some published work available on this. From this data set, it's possible to calculate a release magnitude, and this is around 1.4 times 10 to the 10 becquerels in total. We get very similar numbers using the stacks data, which is measuring the gas as it is released. And now we also have in the field measurements from this type of facility. So we have detections that, following lots of analysis of many detections, and most of them from the background, we're able to determine one that was solely attributed to Hartlepool reactor, and from this calculate a release magnitude which agrees with the numbers that we had from the core itself. Analysing this data set was not easy. There were over 350 detections of xenon-133 on the Sauna Cube array for the year that we were measuring. So just one of those detections was definitively linked to Hartlepool Nuclear Power Station. Over 280 other detections have been attributed to at least one facility. In some cases, we were not able to say exactly which facility it was, rather a group of known operating facilities in a given region. Of those, 195 detections were linked to IRE in Fleurus in Belgium. So this is well known that this is a big source in mainland Europe, and it was expected to dominate the background. And the STAX data that was available from IRE was extremely useful in identifying which detections were from IRE emissions. So a measurement campaign such as this has focused on Hartlepool Nuclear Power Station, but it would not have been successful without this STAX data from IRE due to the sheer number of detections that we were able to attribute to the background. For Xenon 133 detections identified on the array and ATM simulations, it was possible to confirm the total release magnitude, which then agreed well with calculated releases from the source. In the period that we were sampling, the Hartlepool reactors had very few operational difficulties, and as such, there were no unplanned releases of radioxenon. So this confirms a very binary nature of HER emissions, and where we may be tempted to use a daily average for all types of nuclear facility, some facilities, and AGR being one of them, this is not a good model for. That concludes my presentation. Thank you for listening. Look out for our latest paper, which is currently being revised for publication in the Journal of Environmental Radioactivity, and this is a look at all of these measurements, and we hope to publish all of the source attributions that we've been able to determine. If you'd like to get involved in work like this, we're also setting up a new project which is looking at characterizing the radionuclide fingerprint of a pressurized water-cooled reactor, or PWR. This, of course, being the most abundant reactor type in the world, is a lot more applicable to the world as a whole. There's a post available on this, P5.1371. Please reach out to my colleagues from AWE who will be available in person to talk to you about this. Thank you.
Okay, we have to do the questions a little bit differently here because Matt obviously isn't with us, but we have Dan Chester here, who is also involved in this project, who may or may not be able to answer your questions depending on what they might be, who's graciously offered to field some questions. So does anyone have any questions for Dan?
Is he here?
I think